All right. Hi, guys. Welcome to Seoul Machine Learning Seminar Week 3. This is post-recorded like last week. Still haven't resolved the issue with the computer. And also the usual disclaimer of these are not my slides. These are taken from the Coursera machine learning specialization. So credit to the people who made this. And yeah, this video is for educational purposes only. It's for people who missed our previous meetups so they can be up to speed when they decide to attend later. All right, so this week, yeah, we talked about classification. All right. So the example that we gave, or that the Coursera course gave for classification, was predicting sentiment. So predicting whether a rating of a restaurant was good or bad by analyzing the sentences in the review and yeah, trying to classify it as good or bad. So for example, maybe rating a sushi restaurant, and in the review, they might be saying that the sushi is excellent, but talking about other things not being good, like ramen or the atmosphere. So you can even grab the sentences and try to classify particular aspects of the restaurant based on what the reviewer said. Yeah, so for example, like watching the chefs create incredible edible art made the experience very unique. So, you know, classifying the experience as good, ramen, yeah, forgettable, not good, so that got classified poorly, and sushi was delicious. So it's important because when someone looks at a review for a restaurant, maybe they don't care about the ramen, right? They just want sushi and a good experience. Okay, so the idea is taking the reviews and then using a restaurant review app that can somehow turn these text reviews into something more like quantifiable, where you can compare to the other restaurants. So kind of like standardizing it into star ratings for different aspects of the restaurant. Okay, so the way that was proposed is breaking the reviews into separate sentences and then understanding what each sentence is about. Like this sentence about sushi, this one is about decoration, and then based on what the sentence is about, classifying whether it was a good or a bad rating of that aspect of the restaurant. Yeah, so the core building block being taking the one sentence and then running it through a machine learning algorithm that would classify it as thumbs up or thumbs down. Okay. Some other classifier applications. So I just want to touch on the difference between what we did last week, which was regression. So, and even though regression is a specific type of machine learning algorithm, but it is predicting a continuous variable. So for example, yeah, it was prices of houses, which could be ranging anywhere from $0 free to whatever, $1 million, $2 million, and there's just a range in there, and the house could be in that range anywhere. So it's a continuous variable that you're trying to predict, whereas a classifier is not predicting a continuous variable. It is predicting a number of things. Like for example, thumbs up or thumbs down, two possibilities for these restaurant reviews. Other things could be like, say it's looking at pictures and there are three choices of what the pictures could be: a dog, cat, or an airplane. So that's three classifications, and basically a classifier algorithm will assign probabilities to each of the classifications, and then the probability that has the highest, say if dog had 60% and 20% for each of airplane and cat, then it's going to classify that picture as a dog. All right, so yeah, so this is, for example, the sentence review changed into thumbs up or thumbs down, which is the case study that was used in this week. right? Here's another one. There's 3 classifications, such as education, finance, or technology for a website or an article, right? So basically you put in the text of this article, and then the classifier would decide which of these 3 topics it's closest to. Or another, of course, probably the most famous example for a classification algorithm is spam filtering, deciding if an email is spam or not spam. All right, and this would be the image recognition, similar to what I was mentioning, only in this case, the machine learning algorithm, maybe it already knows if it's a dog, and it's trying to classify what kind of dog. And then these green bars would, these would be analogous to the probabilities that were assigned for each of the classifications it's trying to decide amongst, and the number 1 being Labrador Retriever. Another choice, or another kind of application, based on various metrics such as an X-ray, your temperature, your some kind of genetic susceptibilities, and your behaviors. You could predict what maybe what condition a person has. Are they healthy? They have a cold? Well, yeah, just generally some kind of medical diagnosis. Yeah, so okay, let's move to the next one. Yeah, in this one, image classification, deciding you could have people like, you know, basically you would be scanning people's brains continuously as they look at pictures, say, of a hammer or a house. And the, you know, based on matching, like, this picture is of the brain while the person's brain while they were looking at a hammer, and this other picture is what it looked like when they were looking at a house. And you have those kind of pictures for, you know, thousands or hundreds of thousands of people, and then you can train the algorithm to be able to decide. Maybe say you put a new person after you've trained the algorithm, they can go under this same kind of scanning technology, and then you can show the person a picture, and the computer can tell you what they're looking at without actually, you know, being tied to the picture, just looking at the scan of the brain. Okay, linear classifiers. So these are like the simplest kind of classifier. Basically, they can only, linear classifiers are a little bit limited on what they can accurately model. They're gonna have to, the relationship would have to be, well, linear, and for it to be able to achieve results that are useful. So let's look at some examples. Yeah, basically, in a linear classifier, you would have in this example, you have 2 outcomes. Either the sentence is positive or negative, and basically it knows some different positive words and knows negative words, or it learns them rather from examples, and it starts assigning weights to each word, and then based on the counts of each kind of word in the sentence, it will decide overall by multiplying the weights times the count, and then summing for all of the words, and based on the result, will decide whether it's a overall positive or overall negative. So for example, sushi was great and the food was awesome, but the service was terrible. So we have 2 good words and 1 bad. Now, if this weight is huge, so big that it outweighs both of these good, then it's going to classify negative. Okay, so the problems to address with this kind of threshold classifier. How do you get the list of positive and negative words? That's going to be by training. Basically, you're going to train an algorithm, and it's going to be supervised learning. So it means the algorithm is going to have a label in it, and it can look after it, you know, predicts something, and then it can compare its prediction to the label, and then based on the error, it can, you know, back propagate the error to the weights, and then those weights will be changed, and in a way that it can become closer to the correct answer, and it'll iterate like that until it gets correct. Words have different degrees of sentiment, right? So this is where the weights change. The great would have a higher weight assigned than good. And this would also be learned through the machine learning process. All right, but then the thing about this kind of simple machine learning algorithm that can only look at one word at a time, it's not going to capture as much complexity for elaborate features. So for example, not good, which is two separate words, which together mean something negative, it's not going to notice that. It's just going to notice good and not separately. So there will be some limit to what a model that, basically a model that can look at one word at a time is going to be more computationally probably efficient or less computationally heavy than one that can look at, that has to look at two words all the time. But the trade-off is that it's not going to capture that extra complexity necessary, or that it's not going to capture the elaborate features accurately. All right, so yeah, this is what I was talking about. The words get assigned different values. So a higher positive value would be a more positive word, and on the other end, bad, -1, terrible, worse than bad, so more negative. And then there are these kind of neutral words that are just going to appear in all of them because they're just describing, or they're just needed to, so that readers know what the review is about, but it doesn't necessarily have a positive or negative connotation. So those would be 0. Yeah, and then basically you're saying you're setting some threshold. In this case, maybe the threshold is 0, and you're summing up after multiplying. So for example, one time great appeared, so 1.2 times 1. One time awesome appeared, so 1.7 times 1. And then negative 2.1 appeared, or terrible appeared once, which is negative 2.1 times 1. You sum them up overall, it's 0.8, which is greater than 0, so it would be classified as positive. All right. Yeah, so this simple, is this adding more value? No, I'm gonna skip this one. Okay, decision boundaries. Yeah, suppose there are only 2 words. So this is just for a very simple example of a linear boundary. So the weight for awesome is 1, awful is -1.5. Because of the simplicity, we can actually look at each point and we could sum it up if we wanted to. And we would see that, for example, here, 3 awesome, 0 awful. So just 3 times 1.0, 3.0 would be the score, which would be positive. But then let's look at this one here. 2 awesome, which is 2.0, and then 3 awful, -4.5. So that's going to be negative. So basically the line is going to be somewhere in between this one and this one. And that would be the line, the linear, it's called a linear classifier because the boundary between the positives and negatives is a line. But that's just describing the threshold of where you decide which side of the classification to put it on, positive or negative. Yeah, so here you have the line drawn out. And yeah, so it looks like all of these ended up being positive. These are negative. So you could actually, you could go through and sum up and you would find out that this is, these are coming out as greater than 0 or less than. Right, but realistically, most times that you need to use machine learning, you're going to need a more complex decision boundary than just a line. You're going to have these kind of really complex squigglies, or you're going to have like hyperplanes, because there are a lot more than just 2 features. Yeah, so you're going to end up with classifiers such as like decision trees or gradient boosting and random forest, and these are more like ensemble learners that can classify highly complex models or highly complex data sets and relationships. All right, training and evaluating a classifier. Yeah, so basically you have your data and you're splitting it into your train set and your test set, and you're using your train set to learn the classification, and then you're using the test set to evaluate. So there are different ways that you might evaluate. You might have use accuracy or precision, and it kind of depends case by case which kind you would want to use. All right, so this slide is kind of not looking great. We're going to skip it. All right, so here's two examples, error and accuracy. Basically, these are just the complements of each other. Error is a number of mistakes over total number, and accuracy is number correct over total number. So basically, you could just, if you took 1 minus accuracy, you're going to get error. And if you did 1 minus error, you're going to get accuracy. And then the difference being, what's your goal? With error, you're trying to minimize, accuracy, maximize. All right, what's a good accuracy? Also different depending on cases. So if you just guess, you should be able to get, for example, in a binary classification, there's only 2 choices. You should be able to get 50% by just guessing. So obviously a good accuracy should be much higher than that. But then for other K classes, well, yeah, for K classes, the accuracy is 1 over K if you're just guessing. 1 over 3, 1 over 4. All right, and then there's the question, is the classifier with 90% accuracy good? That also depends. You know, because, for example, there are, well, if 90% of emails sent are spam, well, if you just classified every email as spam, you would achieve this, right? So that's not actually good, because the 10% that are not spam would just also go in your spam folder. And then if you're just sifting through your spam folder looking for your emails all the time, how is that different than just not having a spam filter, right? All right, so you got to dig in and ask questions. All right, is there class imbalance? So another example of class imbalance, the spam thing is one. Another one is one that I did. I trained a digit recognizer that was supposed to recognize 5-digit numbers in a picture. But the thing was, out of over like 200,000 pictures, I think only like 20 of them actually had a 5th digit. So if the classifier just always guessed that digit was blank, it got 99-point-something% accuracy on that digit specifically. And even though it was evaluated on having all 5 correct, even though that digit was always wrong, it was still able to achieve really high accuracies. So that's the example of class imbalance. It's kind of like, you know, if you took a test with A, B, C, and D, but you know 70% is A, all you do is just guess A all the time and you'll make 70%. This is another example of class imbalance. Yeah, so how does your accuracy compare to, you know, just random guessing or the majority class? And then also, yeah, what's good for the application of the machine learning algorithm to make it better than an alternative? So just to bring up the digit classifiers again, I believe the digit classifiers, it was claimed in the seminal paper of that kind of technique for deep learning, or that application, that 98% of let's say addresses are classified correctly by human map makers that use photographs. And they were trying to, the reason for this was done by Google, and the reason why they were trying to make this machine learning classifiers is so that it could beat human accuracy. So it would need to be over 98% accurate in order to do that. All right, false positives, false negatives. Okay, so basically a true positive is a situation where it actually is a positive example and the prediction was positive. But a false negative would be it's predicted negative, but it's actually positive. All right, and then down here, the false positive meaning the label was positive, but it's falsely labeled positive. All right, and this one truly labeled negative. All right, so is that, how are these different mistakes, which one's more important? This can also depend on the application. So like for spam filtering, if you like let a spam email through, you falsely label it not spam, it's annoying. But if you put someone's, I don't know, important email from their, say, coworker or their something like that, then they can actually, it being in the spam folder can damage them worse. So a false positive in this case is worse. But then let's say in medical diagnosis, let's say if you're looking at cancer screening, a false negative on cancer screening means the person has cancer, but they might go another year or 2 years with that cancer without knowing, right? And then it could become critical in that time. Whereas if you falsely, let's say they don't have cancer, but it says they do, usually they're with these preventive screenings, the first level is usually like a very cheap test that's not as precise, but then the second level of test is more precise, and but it's more expensive. So yeah, it might cost some money, but that's better than someone dying in that 2 years from cancer that they didn't know they had. All right, so just to give an example of a confusion matrix, the diagonal will be the correct classifications. And so like in this case, in just looking at accuracy, we have 50 true positives and 35 true negatives. So that gives you 85 out of 100. And this is the way the 15% that were wrong are distributed. All right, same thing here. The diagonal is the correct cases. And these are just showing you the nature of the mistakes. All right, how much data do you need? All right, how much data do you need? How much does it need to learn? So generally, the more the merrier. But even though more data will usually improve the model, there will be eventually, no matter how much data you give the model, there will be limitations inherent in the model itself that will mean that, the precision will kind of plateau, or it'll be asymptotic. So it won't reach like 100%, and that's because all models have assumptions embedded in them that's necessary because there are simplifications. So yeah, all models are wrong, but some are useful. All right, yeah, so this is just kind of looking at the relationship of, the error decreasing as the amount of training data, but then this is generally somewhere it will just kind of, stay the same for the most part. All right, so this is just continuing on that. All right, so more complex models will tend to have less bias. So for example, the one that does single words, it's going to have some inaccuracy no matter how much data you give it because it only looks at one word at a time. All right, so it'll never classify not good correctly. But then the more complex model that looks at 2 words at a time, or bigrams, it will be a little bit more computationally heavy. It'll require more data because the learning curve will be steeper. So for like this, basically, it'll need more data to achieve, the same kind of accuracy that the blue line will, that the less complex one, but then in the long run, it'll outdo it with more data. So this can be seen especially in like deep learning. When you're working with deep learning, the networks are usually really complex, and you're gonna have to train it longer and with more data. But once you do that, you can get much higher precision and accuracy, because it can represent much more complex ideas, such as like layers of images and objects in images and even context. All right, class probabilities. All right, so yeah, even though it is classifying into discrete categories, it's using probabilities to do this. And the thing is that there should be a threshold. Like, for example, if it's the threshold 0.5, both of these would be classified as positive. But this is closer to the 0.5 cutoff. So as you get closer to your threshold is where you'll see the more of the errors than up here. Okay, so just summary of classifications. Let's go ahead and just look at what we did with the Zillow data. There's a few. It did not do well because I didn't have the time to put into the feature engineering that I needed to. It was finals week, so I had to put a lot of time in the grading for my students. But it's good enough to just kind of see an example of some of the machine learning concepts that we're kind of learning in this seminar. So the week coming up will be, what are we looking at? We're going to be looking at clustering. So that'll be next week, July 2nd at 8 p.m. in Bitcoin Center, Korea. So hope to see lots of people. While this is loading up, I'll say, yeah, we had one other new person that came up on week 3 for this classification seminar. He has a educational startup in Korea. It's for teaching English using video games. But yeah, we're probably almost done because this Jupyter notebook is quite short. I just want to go over a couple things in here. So for the clustering thing, we might use something other than GraphLab for the upcoming one on July 2nd. We'll have to see. Might use scikit-learn. All right, just navigate to our file. All right, so this kind of usual steps of like importing GraphLab and then So what we tried here is predicting positive or negative log error. And so it was a binary classification. And we're just trying to see if, based on the data as it is, could we get a logistic regression machine learner to correctly, or get some kind of accuracy, predicting whether it would be positive or negative based on the features. As you're going to see, that didn't work. All right, so we loaded our S-frame. If you're looking at the GitHub repository and you don't have this S-frame yet called features with error, it's under week 2. Or is it week 1? Week 2. It's going to be in the week 2 portion of the GitHub repository. All right, so we set our GraphLab canvas to this notebook, and then we take a look at the log error. So log error is what you're trying to predict in the Zillow competition, and the log error of the difference between the Z estimate and the actual sales price of the home, right? And this is basically normally distributed. You got the most here, and slightly skewed in the positive direction. So the algorithm tends to predict higher than what the house actually sells for. But generally, it's normally distributed, and so it's a pretty good. Because it's normally distributed around 0. It means the Z estimate is pretty decent. Okay, so what do we do here? So we split the log errors into overpriced versus underpriced, and this is defined as the log of the Z estimate minus the log of sale price, which is the equivalent to log of Z estimate over sales price. So it means positive log errors are overpriced by Zillow. All right, a 0 log error would mean that the Z estimate algorithm was correct. It was dead on. Maybe the person actually made their offer based on the Z estimate. All right, so we're gonna go ahead and just cut those out. So basically we're saying where log error is not equal to 0 in the features plus error S-frame, we're gonna keep those ones. And the ones that did equal 0 are not gonna make it into our object. All right, so now we're going to create the overpriced feature, which is going to be a binary variable. And if it's 1, it means that the log error was positive. And if it's 0, it means the log error was negative. So we're just saying basically where the log error is positive, insert a 1 in that feature, 0 otherwise. All right, and then now we can just look at the counts to see what kind of percentage we have going on here. So over 55% are overpriced, all right? Less than 45% are underpriced. So what does it mean? It means if we just guessed 1 for everything, we could achieve this percentage accuracy. So just without any kind of machine learning at all. All right, so let's try to train the overpriced classifier. All right, split our data set into train and test, 80% for train data. And then what I did here was I just, using this function column names, I grabbed all the feature names into a list called classifier features. All right, and that length was 54. So we have 54 features. And then what I did is I went through the list and I cut out the ones we don't need to try using on our classifier. So parcel ID, which is basically the key, is going to be unique for every house. Log error, this is what we're trying to predict. This shouldn't be here. Absolute log error is just a transformation of log error. So also cut that out. And overpriced. Yeah, oh, sorry. So log error and absolute log error, yes, we're trying to predict that. So we don't want our classifier to use these variables. And this is the variable that we're trying to predict in this specific case with this classifier. yeah, so that's why these 4 are gone, taken out. I actually tried several things. This is the only one that tried to classify. The other ones would just stop after 2 or 3 iterations because they couldn't really find a direction to move beyond just guessing. This one it actually tried, but as you're going to see, it did not really make useful progress. It's because there needs to be some feature transformations done in order for this to work. Okay, so yeah, shove in the train data to the model, the class, to train the logistic classifier and save it as the overpriced model is what we named it. The target is overpriced, that's what we're trying to predict. Here's our list that we just made, which is 50, just to check our 4 did get dropped. All right, and then using the test data as the validation set. I set the max iterations to 100 because it was not able to optimize. It actually can't on this one either. It says this model may not be optimal. To improve it, consider increasing max iterations. But here's why I didn't. If you look here, if you just guess 1 on everything, it was 55 point something %, right? Well, look here in this training set, we have 56 and here 55. So the value for the whole set is in between these two. So we could say it's probably just guessing 1 on everything here. All right, and then here you can see it's starting to change its accuracy on the training set, but it is not transferring to the validation set. So basically this is a clear case of overfitting. The model's overfitting on the training data, and it's actually losing its accuracy on the test data. So it means even though it's found a direction to try to move on the training data, it's not translating. And it's not useful on the test set. So what does this mean? It means this model is not really making progress. So I could increase the max iterations, but all it's going to do is continue to overfit on this data, most likely, and not improve here. All right, so we can check out the ROC curve, which is pretty awful, actually. This should look more like this. All right, and then, yeah, this is just a show. Like, this model is really, the features need some work done for it to be able to do anything. So, like I said, I didn't have a lot of time to put into it, but it's just to kind of use it as a teaching point. What are some things we could do? Maybe some of the continuous variables, the features, probably we could log transform them to see if there's some kind of skews in the data that might be damaging the ability to train a classifier correctly. There are probably some categorical variables that look numeric. So maybe we should do some one-hot encoding. For the first example that comes to mind is the bathrooms feature. It has like 1, 2, 2.5, 3.75, things like that. So even though those are numeric and bigger does mean more, maybe we should change that to categorical. Maybe that would work better. All right, and then other classifiers might do better. For example, ensemble learners, bagging. Yeah, so these are just some examples, stuff to try. Yeah, that's it. So this was kind of a short one, but yeah, next week we'll do clustering. So see you then.